Hello and welcome. Today, we're diving into a really powerful tool from the world of statistics, the chi-square distribution. Now, that might sound a little intimidating, but trust me, it helps us answer a super important question that pops up everywhere in science. Is what I'm seeing a real pattern, or is it just random luck?
And to really get a feel for this, let's go way back to Gregor Mendel and his famous pea plants. His theories on genetics were revolutionary, and they predicted these really specific ratios for different traits. But when he actually went and counted the peas, the numbers were close, but they were never exactly perfect. And that leads to this huge question. How close is close enough? At what point do you say, yep, my theory holds up?
And that, my friends, is where the chi-square test comes into the picture. It was basically invented to solve this exact problem. It gives us a solid mathematical way to figure out if the gap between what we thought we'd see and what we actually saw is a big deal, or if it's something we can just chalk up to random chance.
Now, let's peek under the hood at the formula that makes it all work. At its heart, the idea is actually pretty simple. For whatever we're studying, we're just comparing O, which is our observed data, what we actually counted, to E, our expected data, what our theory said we should have gotten. This formula just gives us a way to bundle up all those little differences into one single number. So, let's put this tool to work. The first big thing we can do with it is something called a goodness of fit test. And honestly, there's no better example than going back to Mendel's own data. We're going to use the chi-square test to find out if his real-world results were actually a good fit for his amazing theory.
Okay, so what was the hypothesis we're testing? Well, in statistics, we always start with what's called a null hypothesis. Think of it as the default idea or the claim we're putting on trial. In this case, our null hypothesis is that Mendel was right on the money, that the p's will follow that perfect 9:3 to 3:1 ratio.
First things first, we need our O, the observed data. This is the real deal. This is what Mendel actually saw when he counted his peas. 315 were round and yellow, 108 were round and green, and so on. A grand total of 556 peas. This is our reality check.
All right, now for the E, the expected data. If Mendel's 9:3 to 3:1 theory was absolutely perfect, how many of each type of pea should we have seen in that batch of 556? Well, we just do the math. For example, 9/16 of 556 is 312.75. We do that for all four types to create this picture of a perfect theoretical world. Now we start plugging things into the formula. First, we just find the simple difference, observed minus expected. You'll notice some numbers are positive, some are negative. To get rid of those pesky negatives, and also to make bigger differences count for more, the next step is to just square each of those results.
We're on the home stretch now. For the final step, we take each of those squared differences we just calculated and we divide it by the expected number for that group. Then, the grand finale. We add all four of those results together, and that gives us our final chi-square value.
And here it is, 0.469. This one little number neatly summarizes the total amount of difference between Mendel's real data and his perfect theory. But here's the catch. Is 0.469 a big difference or a small one? On its own, this number doesn't really tell us anything. We need something to compare it to.
And that something is what we call a critical value. You can think of it like a statistical line in the sand. We get this number from a standard chi-square table. To know which number to look up, we need our degrees of freedom, which sounds complicated, but it's just the number of categories minus 1. So we had 4 types of peas, which means we have 3 degrees of freedom. And for this test, that gives us a critical value of 7.815.
This is the moment of truth. Our calculated value, 0.469, is way smaller than that critical value of 7.815. And the rule is simple. If your number is smaller than the critical value, the difference isn't statistically significant. It's probably just random noise, so we accept the null hypothesis. The verdict is in. Mendel's data is an incredible fit for his theory.
Okay, so that was pretty cool, right? But the chi-square distribution has another awesome trick up its sleeve. It's called the test for independence. The question we're asking here is a little different. It's not about how well data fits a theory, it's about whether two completely different things are related to each other at all.
So let's dream up a new experiment. Imagine we're studying some organism, and we want to know, does the temperature it lives in have any effect on its physical appearance, its phenotype? Are these two things, temperature and phenotype, connected in some way, or are they totally independent of each other?
For this kind of question, we organize our data in what's called a contingency table. It just shows us the counts for every possible combination. So you can see, at 30 degrees, we found 80 with the dominant trait and 30 with the recessive. Down at 15 degrees, we found 90 and 20. Now, we could go through that whole process of calculating expected values like we did before, but for a simple 2x2 table like this one, there's actually a handy shortcut formula. It just uses the values in the 4 main cells, which we label A, B, C, and D, and lets you calculate the chi-square value directly. It's a real time saver.
After we plug our numbers from the table into that formula, we get a chi-square value of 2.59. And just like before, this number is kind of floating in space. We need to know, is this a big enough number to suggest there's a real link between temperature and appearance?
So you know the drill. We head back to our chi-square table. For a 2x2 test, the degrees of freedom is always 1. And at 1 degree of freedom, the critical value, our line in the sand, is 3.841. Okay, let's make the call. Our calculated value was 2.59. The critical value is 3.841. Our number is smaller. So what's our conclusion? We have to say that we don't have enough evidence to claim there's a connection. Based on our data, temperature and phenotype appear to be independent.
So let's zoom out and really nail down the big idea here. The fundamental power of the chi-square test is that it gives us a clear, objective way to separate random, meaningless little wiggles in our data from a result that is actually significant and meaningful. The beauty of it is that the logic is always the same. You start with an idea, a hypothesis, you go out and collect your real-world observed data, you figure out what you would expect to see if your idea was true, you crunch the numbers to get that one chi-square value, you compare it to the critical value from a table, and then you make your decision.
I think this quote just says it all perfectly. A really good way to think about your chi-square value is as a deviation score. The bigger that number gets, the more your real-world data has strayed from what you expected. A really big score is a red flag that something more than just random chance is probably going on.
So why does all this matter? Because it takes us beyond gut feelings. It gives us an objective way to test our ideas. It's a cornerstone tool in everything from biology and medicine to psychology and marketing. But, and this is a really important but, it only gives you reliable answers if your sample size is big enough. You can't do this with just a handful of data points. So the next time you see a pattern out in the world, maybe it's in a news report or something you notice at your job, ask yourself that chi-square question. Is this a real, significant pattern, or could this just be the random static of the universe? The cool thing is, now you have a mental tool to help you figure that out.